All right, welcome everyone to the AI-SDM seminar. Today it's our pleasure to have Nikhil Garg here. He's an assistant professor in the Operations Research and Information Engineering Department at Cornell Tech. And he uses algorithms, data to study societal systems, so clearly very relevant to the mission of our institute as well. And I've been waiting to hear more about what he does for a while. He has many accolades. He received the SF Career Award, the Informs George Danzig Dissertation Award, an honorable mention in the ACM SICOM Dissertation Award, many other paper awards, as well as the Forbes 30 under 30 for science. Yeah, all right, take it away.
Great. Yeah, no, it's great to be here. Sort of I've watched afar from this institute, sort of know a lot of people here. Yeah, it's great to be here. I apologize for the, and I tell my students this, like my class is called this, my PhD class is called the same thing, Engineering Societal Systems, which is very egotistical, sort of like who are we as engineers to engineer societal systems. But I think it's apt to sort of as a descriptor of what many of us aim to do in settings where this is possible. And so, I think maybe everyone here has seen different versions of this flow chart, but I still like starting sort of talks like this, which is, there's a lot of stages of doing a good job with a computational system in the real world, right? From problem definition to data generation, predictive modeling, how do you turn predictions to decisions, deployment and evaluations. And then sort of what I'll focus most of the talk today on is sort of trying to understand sort of societal level effects, societal equilibrium. And much as like while all of us sort of know that there's this entire pipeline, this is one of my favorite plots from a paper. It's not one of mine. It's a few, CMU connections, Emily Black, Ravi Ghani, Hoda Hidari, which is sort of showing, this is in the context of algorithmic fairness, but sort of the vast majority of sort of research is focused on a very, very narrow part of this pipeline, right? Is sort of our own statistical modeling, and in particular trying to mitigate disparities. Sort of this in the context of algorithmic fairness, trying to mitigate disparities, but sort of maybe problem formulation, data collection, deployment integration, sort of other aspects of problems behind mitigation is sort of, I think, relatively understudied. And I think sort of, it's on all of us to maybe change this plot for when it's hopefully, or I guess hopefully not replicated 5 years from now. And so I think I thought I would give an overview of my attempt at sort of working on every stage of this pipeline, including predictive modeling, but sort of especially as it connects to the other pieces in this pipeline. So a lot of my work, and I'm not going to talk about this today almost on purpose, because I feel like this is the stuff closest to a lot of people in the Institute, is sort of trying to understand how does human-generated data bias prediction, right? So I'll talk about this, very briefly in a few slides, but sort of trying to understand, for example, if data is systematically missing from certain populations, how does that affect our predictions for downstream outcomes? And sort of working on this in the context of crowdsourcing systems, and then also sort of in health, where sort of we might not have as accurate race data as we might want. But sort of the predictive modeling stage, we're not done at the predictive modeling stage. A big line of, I think, sort of where I'm especially interested nowadays is how do we model errors in machine learning models as they affect downstream outcomes. So as a very simple example, this is one of my sort of a really fun paper we worked on recently. Sort of we're showing that because your recommendations are uncertain, right? Because your estimates of how much someone likes something is uncertain, you should naturally diversify your recommendations when giving a set. Why is that true? Is because if you don't diversify and you sort of give the 10 items you predict they're going to like the most, well, if your errors are probably correlated, right? You're probably going to give them very similar items. And if they don't like that type of item at all, sort of suddenly you didn't give them anything you wanted. And so sort of like these simple models of trying to understand, okay, any prediction has errors. How do these predictions structurally change sort of decisions you need to make, not just at the individual level, but when you're making a set decision. And then this is what I'm going to sort of spend a good chunk of time today talking about, which is sort of how do we go beyond understanding a single decision, right? So in many of these settings that we might care about, so in education and labor market and all sorts of things, you as the algorithm designer are not just are not just giving recommendations or doing something for one person, you're doing it for 100 people or 1,000 people or the entire population at once, right? So how should you think about equilibrium effects, population effects, in these settings? What does it what does social good mean sort of when you have to sort of take it through this like equilibrium transformation? And then what I'm really what drives me nowadays when thinking about new methodological questions is application. So sort of how do we design and evaluate real world systems in practice? And so I talked about this with various sets of you sort of this morning and last night, but sort of from understanding crowdsourcing systems to sort of, I'll talk about a few today in terms of applications, working with an admissions team, and sort of also discharging patients from hospitals. And sort of, yeah, a lot of this work sort of, I firmly believe, you know, maybe this is the wrong crowd to preach to, but sort of I firmly believe that good methodological questions come from working with practitioners from a very precise sort of, I was describing to someone today as sort of this inductive deductive process, right? Is you sort of, from a very precise setting, you think of what are useful methodological questions to solve, but then suddenly you see that methodological question in 20 different applications. And again, you know, I have this slide in the beginning of a lot of my talks, so maybe this is again preaching to the choir here, but I think now is the perfect time to do a lot of this work. I think for three reasons that are kind of interlocking. The first is, you know, it might not seem like this, but if you like look around, we really have way more large, granular, open data sets in real world settings than we had even like 10 years ago, right? So I used to joke, I don't think this is quite true anymore, but I used to joke that sort of my tenure case will be made up on just using the New York City Open Data Portal. And that's like still like 80% true. It's like now use the Chicago Data Portal too, but right, but like sort of there's all this sort of in quite important settings. A lot of government agencies, a lot of nonprofit, a lot of places are sort of often freely sharing pretty important administrative data that you can get like even 80 or 90% of the way they are doing something cool, even before you really partner with practitioners. And then sort of two is, you know, of course, we have this really great modern computational sort of just toolkit to think about problems, sort of across algorithmic fairness, ML, AI, you know, all sorts of things. And so what's nice about that is not only we have this language to think about important problems, but, you know, at least in academia now, I don't think you really have to worry much about getting good academic credit for this sort of work, right? It's like maybe 10 years ago, you have to worry like, well, people appreciate it. I think now that's like, you know, kind of a defunct concern, at least in my mind. And then perhaps most importantly, there's a lot of people out there who recognize the importance of sort of computational social good work in their systems. And so if you find the right people and they exist, sort of there's important decisions to make that you can sort of help steer. And then sort of, it's kind of called challenges because I like the symmetry of opportunity and challenges, but I think sort of from an academic's perspective, these are also an opportunity, right? Is sort of, there's like good methodological challenges that sort of, if like what you care about is solving good like methodological questions, there's all sorts of, you know, of course, you know, to this crowd, I don't need to sort of belabor the point of missing censored, unreliable data and the importance that has for predictions. What maybe I hope to convince you of is sort of the other side after you do predictions of sort of the decision effects, societal population, equilibrium effects. Sort of both of these things are perhaps equally important. And then especially sort of, I tend to think a lot of these questions are wide open because a lot of our ML language to talk about these things sort of weren't developed for the high stakes applications a lot of us have in mind, right? It's Like nowadays, I think a lot about recommendation and matching systems, and this was all developed for like Netflix sort of movie recommendations, right? And if that's where the literature was developed, there's just gonna be a lot of, I don't know, maybe low hanging fruit's not the right word, but sort of things that just naturally don't come up in those systems that sort of are first order in these systems that we might care about. And sort of, but I do think sort of to take best advantage of this, it's important to have intuitions across research fields. Okay, so like sort of enough of preface. That was maybe slightly longer than I thought it would be, but so for the rest of the talk, what I'm going to do is give a few minutes on sort of one example of sort of the type of domains and the questions I've been working on in terms of allocating government services efficiently and equitably. And a lot of this stuff, not all of it, but a lot of this stuff was like in the first type of part of the pipeline that I showed is how do we sort of take into account data biases to make either good predictions or good decisions in ways that are efficient and equitable. And then for the remainder of the talk, I'm gonna sort of switch over to a more recent obsession in terms of recommendations and matching systems, which is to first order and more focused on the second half, is like, given we have predictions of some erroneous quality, sort of how do we turn that into making effective recommendation or matching decisions? Happy to pause here, mostly because I need water. There was something in the chat, but I don't.
Oh, it was just me asking.
Oh, okay.
Yeah.
Great. Any questions or thoughts? Or I haven't really said anything yet. So. Okay, great. Okay, so the first line of work is broadly on understanding government services with a whole bunch of sort of students and collaborators, other faculty collaborators, and sort of especially close collaborators in the New York City Department of Parks and Recreation. And so the context is what I always claim in talks, and no one's called me out as being incorrect, is perhaps the world's largest crowdsourcing to decision-making system, right? So a lot of cities around the world, including New York, most large cities in the United States, have a phone number and app that you can do to complain about things, right? So potholes, trees about to hit power lines, flooded roads, like things that have a certain, like you need fixed either on the order of hours to many years, right? And so New York City's 311 system receives about 3 million requests for things getting done a year, right? From planting trees to fixing this pothole to sort of making sure this fire hydrant doesn't leak. Right, and this is really the primary way that the government is learning about a lot of problems, right? So New York City has several thousand miles of road. It has like 800,000 trees, not counting trees in parks. So just 800,000 trees lining the roadways. There's just like too much to do surveillance on, except through human crowdsourcing. And so this is both urgent stuff and routine stuff. And, you know, there's a long pipeline from something happening to something getting done, right? So like an incident happens, and then hopefully at some point the city hears about it. So for rough numbers, the agency, sort of the subunit of the agency that I work with is like roughly 100,000 reports a year. They're going to inspect about 2/3 of them. So like literally send out a trained forester to the location of the report, and they like fill out this like long form that's like a lot of training for like what's happening at this location. And of the things they inspect, about half the time they'll actually have a maintenance crew go out and fix whatever sort of caused the problem. So whatever problem there was. And there's, you know, perhaps unsurprisingly, inefficiencies and disparities in every stage of the pipeline. So what you're seeing here is, I think sort of 2017 to 2020, each set of bars is a borough. So like a large neighborhood in New York City, Manhattan, Bronx, Queens, for example. And then each color is one stage of the pipeline. So red is our estimate, turns out non-trivial to estimate, I'll talk about that in a second, from incident to report, so the incident happening to the report being generated. Blue is the time from the report to the inspection, and green is inspection to work order.
Is this conditional on each of those stages?
Yeah. Great. So this is the entire plot is conditional on highest priority incidents. That the conditioning is actually the other way, where it's like highest priority as determined by the inspection, but conditional on being highest priority here, it basically always gets done. Right, so it's like conditional on this, but then that gets backfilled. Great. Right, so there's differences in sort of each of these stages, and when it adds up, sort of Manhattan, the richest, most densely populated, sort of has an end-to-end delay of like about a day. And Queens, about 15 days.
This is all for trees?
Yes, so yeah.
So is there like, how many trees per capita are there across the boroughs? Is there some difference there in terms of?
Yeah, so sort of but this is sort of at the incident level.
The
Yeah,
more trees there are, the more incidents, like, I guess that's what I'm trying to figure out, is it like in Manhattan, there are just way more people per tree? So you're more likely to catch an incident, or?
Yeah, good question. So like, in our work, we sort of do a lot of like socioeconomic correlates of reporting behavior, sort of, and certainly like whenever you do that, and it's always a great sanity check, is like population density is like, the more dense it is, the faster reporting behavior, like more reporting that's gonna happen. And so that's certainly sort of what's causing, causal, nothing we're doing is causal, but yeah, that's certainly, I believe, contributing to like Manhattan being much smaller than like the other boroughs here. But even sort of after the reporting, the other stages also are. And I'll show you a map in a second, which is even taking away population density, the effect of the other socioeconomic characteristics. And so our research agenda here was trying to understand sort of this reporting behavior first, and then understanding and improving decision-making, sort of given the report. Now, we immediately run into a problem when saying we want to understand reporting behavior, right? How do we distinguish underreporting from a neighborhood truly having a fewer problems, right? It's like, if a tree falls in a forest and no one reports it, sort of what do you see in your data? And this is a fundamental problem across a whole bunch of settings. It's called the benchmark problem. And policing, you might want to audit disparate policing, but you have to be worried about sort of differences in crimes committed versus inequitable policing. And healthcare, sort of under testing versus the population just having better health. Where a lot of the math was developed was actually in the sort of Bayesian statisticians in like the 50s and 70s, sort of wondering about ecology. So like, how many animals are there out there versus how hard did I try to find that? And so a big chunk of our work has been trying to basically identify, sort of getting around the benchmark problem in different settings using different identification strategies. And now I'm going to do like one paper, one bullet point, just because I want to move on. So sort of the first thing that we did was we wanted to understand reporting rate. So exactly that thought that I showed you in the previous slide is what is the delay between something happening versus getting reported. The key idea there was we have duplicate reports made by different people for the same incident. And so sort of you have to like be careful about like facade windows where you estimate things, blah, blah, blah. But essentially you can use duplicate reports or the lack of duplicate reports to measure the reporting rate conditional on the incident happening. With essentially the idea being the delay between the first and second report tells you something about the delay between the incident happening in the first report. The second idea was for whether incidents were reported at all. And sort of the idea here is that for incidents like flooding, you know that incidents are spatially correlated, right? You know that if this neighborhood flooded, that increases your posterior for the surrounding neighborhoods to be flooded. And maybe by assumption, reporting is not spatially correlated, but is demographically correlated or socioeconomically correlated. And so these two things are not perfectly aligned, they are correlated, but they're not perfectly aligned. And you can use the difference between them to try to understand reporting rates sort of at all, sort of as a function of socioeconomics. And then finally, this is more recent work. In many of these applications, you actually can go out and get relatively unbiased data using random or proactive government inspection. So the city of New York inspects every tree every 7 years. And sort of every restaurant gets like randomly inspected for rodents, like roughly every year, right? And they do them in a block by block manner, and they do them roughly, maybe some are random, some are proactive, but at least not responsive to reports. And you can sort of use them to give you unbiased data. And then how can you leverage this unbiased data to understand reporting rates?
What does proactive mean here?
Yeah, so the city of New York just conducts on a schedule inspections of every restaurant, every tree, every street, every X years. And
Deterministic.
yeah, it's not random, they're not flipping a coin at the restaurant level, but they are saying this entire block is gonna get inspected this month. Yeah. And so then you sort of use these identification strategies, the fact that you have millions of reports across hundreds of types over many years, and basically all of this data is on open data. And sort of a consistent finding is that across incident types and methods, there are socioeconomic disparities in incident reporting. And so with the magnitude and so on, exact numbers differ by analysis, of course. But this map is, if I take away population density as a predictor, and I just project all the other socioeconomic predictors of reporting rate onto the map, sort of what do I get? And sort of for those of you familiar with New York, this is the rich part of New York. Sort of this is the Bronx, this is Harlem, sort of relatively poorer part of New York, sort of very well tracks. What you can point out specific neighborhoods. Basically, any analysis method you do, Columbia pops out as a very high reporting rate. I live right next to Columbia, so I like pointing that out. Yeah. But yeah, this is, this is like a bad outcome of the system, right? It's like very classic, like if more reporting is happening in richer areas conditional on incidents, then that's gonna have downstream impacts on what work gets done. But of course, and I think this is where it's good news for us academics, is there's a lot of methodological work to be done here, right? It's sort of like actually disentangling reporting rates from things happening is a question where, people with our toolkits can come in. And then, so that was sort of the first stage of can we understand reporting rates and how they differ conditional on incidents? But then you might wonder, sort of, can you make better decisions? What do decisions look like conditional on reports, right? Is the agency inspecting the right incidents under some efficiency metric and some equity metric? And what's interesting is the agency does have promises for each incident type. You can go and just download this data set right now. Every agency for each incident type promises to the public how long they're going to take to sort of address the issue, right? And they make this public, it's a downloadable CSV. Now, if you talk to any of the agencies, they have no idea where those numbers came from, and they don't actually follow them, right? They're like very old numbers. And so what you have here is for one type of incident, in blue, the response histogram in the Bronx, so a relatively disadvantaged area of New York, and in yellow, the response distribution for Manhattan. And so this is 0 days, this is 50 days. And this red is the service level agreement that the city was technically promising everyone. Right? But okay, so they're probably not meeting their service level agreements. It kind of looks like there's some differences across neighborhoods. But so what, right? It's like, how do you actually optimize? Like, what do you actually optimize? How do you potentially change this? So sort of what we did in this project was, what we tried to say was service level agreements are a consequence of two things. The distribution of incidents coming in and your budgets and priorities for which things you're gonna get in sort of resolve in each location. And so if you if you optimize for budgets and priorities, you can meet different sort of types of service level agreements and sort of optimize whatever efficiency equity metric that you care about. So we ended up doing this, and basically what sort of the punchline of what we found, and I really like this because I think this is true, is sort of in this setting, there's very little efficiency equity trade-off. What do I mean by that is things that are inefficient are inequitable, and things that are inequitable are inefficient. And to first order. And why is that true? Is because it's really inefficient to just leave a bunch of incidents on the ground in some location, right? It's like no loss function is going to do that. And so we ended up redesigning service level agreements. It's like, you know, in this type of work, it's always a question of, does it actually make any difference to the real world? We're talking to them, we'll see what happens. But sort of the idea is that you can sort of make pretty substantial improvements on historical behavior by slightly tweaking budgets and priorities. What we have deployed so far is like a data dashboard, sort of trying to take all of these estimates that we're doing in various ways to sort of at least give the managers the sort of in the department sort of a visual what's going on in each sub office that they manage.
I'm not fully following, so why do you think the response time is high in Bronx and Manhattan?
Yeah, so I mean, I think this was sort of, I mean, this is a little historical and probably unfair to them, but I think it was basically just budgets, right? Like how many inspectors do they have in the Bronx versus how many inspectors do they have in Manhattan?
Okay.
But I also want to point out, it's not clear that this is bad, right? In the following way, right? Manhattan just has way more people by density, right? I think you can write a perfectly legitimate objective function in which you sort of write down risk days felt by each person for bad incidents. And that objective function would give you something like this, right? And I think that's sort of like that's been reemphasized to me again and again in this work. Is like we can sort of write Pareto curves all that we want, but sort of what the objective the Pareto curve is on is out of our control and the most important thing.
Following up on that, is there anything about density that makes it easier to respond to an incident because like the trees are next to each other or something, or is it not really?
That's a good question. I actually don't, I mean, like, there are aspects of easier and harder. Like, is it in like a forested area in a park, or is it like on the street? I don't know how that correlates with density.
Another potential thing that does correlate with density is just the public pressure, like in Manhattan, if a tree falls,
Yeah.
1,000 people call and from
Yeah.
1,000 people call.
Yeah, exactly, right, yeah, so there's all sorts of reasons that like, I think population density explains sort of at least responses. Actually, we were just talking to them last week. Historically, you could request through the 311 app that that sort of the agency planned to tree wherever you wanted it planted under some zoning laws. And just last week, they were like, and it used to be that like you could request it and then like council members would pressure them to like plant some trees faster than other trees and so on. And just last week, they were like, you can't request a tree anymore to be planted in New York. They're just gonna do a block by block, like every 7-year cycle. They're like, we're gonna go on this block and just do a full planting that we care, but that like we wanna do and then move on. Right, so at least in some cases, they are sort of responding by just like getting rid of service requests. Other thoughts or questions about Sorry, I went through like 5 things very quickly, so I've never given it, so I was telling Brian this last night is. The style of talk I've given so far has almost always been like an OR econ style where I talk about one paper the entire time. And this is my first attempt at the other style. And so maybe, y'all can tell me afterwards if it was too much. But yeah, any thoughts or questions about sort of this agenda? I was gonna move on to thinking about very different style of system recommendations and matching systems.
So
Yeah.
just, yeah, curious on your last point, if that's the solution, right? Like, I mean, I guess they're trying to be equitable by doing that, right? Versus meeting needs of some kinds, right? So were the officials not convinced to like actually like operate on them?
Yeah, that's a good question. So I think for tree planting, their argument is that sort of requests were inefficient and inequitable, right? So for tree planting, they internally have sort of essentially for them, the primary important, like they have a sense of where it's important to plant trees. It's primarily through like heat vulnerability indices to sort of prevent urban heat islands, right? So they have a sense of where it's important to plant trees. They have a sense of where it's possible to plant trees. And so at least their articulation was that sort of service requests and government pressure and like, elected pressure from electeds is only a distortion of now, of course, people who believe in like the importance of preferences and democracy and so on could like argue again, but like at least that was their view, is that really for planting trees, the public is a distortion. Now, you could imagine for other, I'm putting words in their mouth, but like that was what I interpreted. For other things, I think you could argue that that's not true. Okay, then I'll move on to sort of talking about, I think this thing that has been on my mind recently, which is recommendations or matching in high stakes settings. And what I mean with that is sort of these two systems simultaneously that I want to sort of argue are really the same system. So on one hand, you have like traditional Gale-Shapley matching sort of systems developed by Econ CS people, right? So residency matching, runs yearly, assigns doctors to residencies. In places like New York City, middle school students and high school students are matched to schools by sort of these matching systems. And on the other hand, you have recommendation systems in machine learning, right? So think Netflix, matrix factorization, sort of learning preferences from data, and then giving people sets of whatever items to consume or potentially consume. And what I want to argue is that these are really the same system, because what you're doing is you're taking preferences or estimated preferences of people, you're giving them something, and then societal matches get realized, right? And there's some differences, right? So in residency matching, it runs offline, it's once a year, it's a very old school system. And in particular, you sort of roughly assume that every participant has the possibility of seeing and ranking everyone on the other side that's relevant, right? That's a central assumption. And then the participants give the algorithm their rankings, which are then treated as ground truth. And then the job of the algorithm is deciding who gets what, right? Under some, many desiderata, stability being the primary one. Now, matching systems are, the opposite on each of these dimensions, right? They run millions of times a day. You have millions of participants. So think like a labor market, like Upwork giving job recommendations, or LinkedIn giving job recommendations to people, or people to hiring managers. Millions of participants, you can't possibly give rankings on the other side, right? So the job of the algorithm is to estimate everyone's preferences, and then usually give roughly naive suggestions given the estimates.
Is also a key difference that the left-hand side is a two-sided constraint where like each school is assigned 50 students and each student is assigned to one school, whereas the right side, Spotify can
Yeah.
recommend Joe Rogan to everyone.
I think that's historically true. But my claim is that, well, that's not true anymore, right? Is these systems are being deployed in settings where you have two-sided preferences and constraints, right? Now, every online job platform, dating platform, housing, they have healthcare, sort of you can find therapists online through recommendations, right? Every platform has a recommendation system behind it. And these are all settings that look exactly like the assumption, right? They have two-sided, they have constraints, and sort of then the high-level question is how do you incorporate market design ideas, so Desiderata like stability and two-sided capacity constraints into these recommendation systems?
I think Netflix, Spotify, YouTube, they have like a constraint on how many users their recommended video.
No, so I'm not claiming Netflix, Spotify, or so on does this, but I'm claiming a job platform should do this, right? It doesn't help anyone if 1 million people apply to one job. And it doesn't help anyone if 1 million people ask the same freelancer to apply to their job. Right? It's the freelancer is not happy, the jobs aren't happy. Right? So the claim is this wasn't true about 10 years ago in the traditional applications, but in where recommender systems are being used today, you have the sort of constraints and desiderata that you have in matching. And it's also true in the other way, is where matching systems are being used today. So like I said, New York City high school matching or middle school matching, there's 800 high school programs a middle schooler can apply to. And there's a lot of reason to believe that sort of people can't search through 800 programs and construct a ranking over 800. And they can't even apply to 800, but they can only apply to 12, right? There's a lot of reason to believe that humans can't fully rank or even form preferences over the other side. And so for that side, then the question is, what is the role of noise and machine learning recommendations in these historically offline systems?
One distinction, I guess, I'm not quite sure about is, like in residency in high school, you get what you get, right?
Yeah.
Magic system runs and then you have no recourse. But
Exactly.
I guess a recommender, I don't know what the jobs dating examples are like, but.
Yeah, so I think that's a great difference is sort of in these systems, you get matched to something. Now you can always leave the system, right? So you can always be like, you could be like, well, I don't want to go to high school in New York or public high school in New York City, but you can't, to first order, you can't be like, well, I really want to go to this other high school. Yeah. Well, but I think that's interesting because I think some recommendations sort of sites in these settings are sort of mimic something like that in the following way. So like there's some dating apps, for example, that show you a set number of people every day, and that's who you have that day. Sort of you can sort of for that day at least, you can't be like, show me 10 more. Yeah, so sort of this picture, sort of a lot of the projects that I'm starting now is either how do we take ideas from here to here, or how do we take ideas from here to there. What I want to spend a little bit of time on, sort of this is the one paper, or I guess 2 papers that sort of I'll go in some amount of depth today, is this line of work of studying algorithmic monoculture in matching markets. So this is with my PhD student, Penny Peng, sort of split across 2 papers, one in NERGS this year and one in EC this year. So the central question was posed by John Kleinberg and Manish Raghavan in this really nice 2021 paper, which is the following, which is, firms are using, so when we say firms, think like people who hire people or people, or admit people, schools, whatever. People are using, as a fact of life, algorithms to screen and rank people on the other side. What happens when a bunch of firms use the same algorithm or the same type of algorithm? Right, so maybe you could say that some applicant has a true value B, And firms are gonna rank according to V plus some noise, right? Because machine learning algorithms are noisy. And maybe what we call polyculture is that the noise is independent across firms, right? So it's like interviews, for example, potentially. Or you could say monoculture is this noise is shared across firms. So conditional on ground truth, firms have correlated noise. And so that's like they're using common test scores or a common algorithm to rank applicants. And then the question is, what happens when you move from this world to that world? And so John and Manish asked this question, and sort of the literature has come to two answers. In John and Manish's original paper, sort of what they said was firms can make worse decisions compared, right? So if firms are making correlated decisions, then as a whole, they're making worse decisions. Why is that true? Because if one of them messes up, then everyone messes up. And then the literature sort of beyond that sort of added to that, well, not only are firms worse off, but applicants are worse off too, right? It's like you're systematically excluded. If one firm rejects you, that means everyone rejects you. And sort of what our observation and sort of our starting point was, well, this literature is ignoring two-sided preferences. It's ignoring two things. Yeah, one is two-sided preferences, which is firms have preferences over applicants, but applicants also have preferences over firms. And all of these models were roughly in a one applicant, two firm model or two applicants, two firm model, right? Whereas real world markets have many, many applicants and many, many firms. And what we find is when all you do is you add these two, so you take the same exact model, extend Manish and John's paper, and now you add two-sided preferences in many, many firms, you get the following results. First, and this is nice because John is Kenny's co-advisor and John and Manish are friends, is the first result is John and Manish were right, right? Is sort of you can fully strengthen their result that with many firms, polyculture, sort of independent decisions gets you sort of this wisdom of the crowds effect. Firms make perfect decisions. And with monoculture, they don't, right? So maybe John and Manish were more right than even they knew. On the other hand, sort of, maybe this is a more aggressive way to say it, but everyone else on the applicant side, were potentially missing something important, which is what we find is just adding these two characteristics means monoculture improves overall applicant welfare. That sort of conditional on applicant true value V is where there's heterogeneity, but so you improve overall applicant welfare, and it's more robust to disparities. And so hopefully in like 5 to 7 minutes, I can convince you that this is true. In pictures. I presented this in an econ theory seminar like a month ago, and I did more than pictures, but today I'll just do pictures. Okay, so this is the model. So you have an applicant and you have a bunch of firms. So this is the original model. You have an applicant, you have a bunch of firms. And polyculture means you might be accepted by some, rejected by others. Monoculture means that you might be rejected by everyone. Right, and so this is the original sort of intuitive belief that this is bad for applicants, right? This means that you might have more systematic exclusion. Why is this not true?
I didn't follow. A, you might be accepted by everyone, and B, in this case, firms now might give offers to more people as well.
Great, so, okay, great. So in monoculture, you're either accepted or rejected by everyone. In polyculture, you'll be rejected by some, accepted by the others. And what you want, and sort of the intuition from the prior work was, well, this world is better, right? This world means everyone's, you're more likely to be accepted by one firm. And if your objective is not being rejected by everyone, then you would rather live in a polyculture world. But I think what you just said at the end is exactly the effect that's missed, is some sort of equilibrium effect.
Yeah.
Right, so the original argument goes is, well, in this world, you're more likely to be rejected by everyone. You're more likely to be systematically excluded. And then the key insight is that this is not going to happen in equilibrium. In equilibrium, similar number of people should get hired overall because firms do yield math, right? Firms do math on how many people are actually going to show up if you give them an offer. And so let's maybe do that in slightly more pictures. Or yeah, so sort of then the claim was that if you incorporate these sort of market level effects, in particular, we have equilibrium as through a Gale-Shapley sort of type setup. What you get is the type of results that we just said. So for those of you who work in these like large market models, we use at this point the classic Azevedo-Leshno sort of continuum model for stable matching. If you don't know what that is, don't worry about it. It's essentially the idea is there's some large number of students. Mathematically, we have to have uncountably many students in the model. You have a finite number of firms, and then all of our math, we're going to take the limit in the number of firms. In the first paper, and then we extended this in the second paper, we're going to say students have uniform at random rankings over firms. And then the true preferences of firms depend on student valuations V. But what firms are doing is they're actually ranking people with noise, right? So this is exactly the setup that I sort of gave the intro with is you're in some stable matching setting, but now you have noise, right? So firms, instead of knowing true value V, have V plus noise, where noise comes from some distribution. And then we analyze the stable matching that results from these estimated preferences. And the intuition is the following, that when noise is independent, whether you get hired at all depends on your maximum score, right? It's roughly, especially in the symmetric setup. In monoculture, you only get one draw, right? You get one draw of this noise. And so in polyculture, applicants get more lottery tickets. But if applicants are getting more lottery tickets, then firm admission standards have to be higher in equilibrium, right? Because they have the same capacity constraint in both worlds. And basically all of our results follow from this basic fact, right? And the proof strategy then, and this is sort of where Kenny's brilliance comes in, is he knows how to reason about max order statistics better than anyone. Right, and sort of basically everything boils down to looking at what the distribution of the max order statistic is. And so the same thing in pictures. Let's say this is your score, you have score 1, and this is score 2. So this is scored by firm 1, this is scored by firm 2. And they're correlated because of V. Right? And these are the cutoffs. These are the set of people who get offers from both worlds, from both firms. This is just firm 1. This is just firm 2. So this is the set of people who get at least one offer. And this is the quantity that has to be constant between the two worlds because of yield math. And in particular, these people receive at least one offer, but they might not receive the offer from their favorite firm, right? They might be here when really they wanted to be there. Whereas monoculture, let's say both firms are using score 1, right? These are the set of people who receive offers from both firm 1 and firm 2. It's the same set. And in particular, the cutoff has to go down because the number of people accepted to either firm needs to remain constant. And so now, if you're in this half, you get accepted to both firms, and you get to go to whichever one you like. And if you're in this half, you get rejected from both. But the people in this half are the same as the people who got rejected from both in the other world. And so sort of all of our theorems then boil down to different ways of saying those same facts, which is under independent noise, firms hire the right applicant. You actually converge to a fully noiseless market. But that's not true under monoculture. Let's skip this. On the other hand, applicant welfare is higher under monoculture than polyculture. Which is basically saying that by assumption, the same number of people receive a match. But conditional on matching, you're more likely to receive a match with your favorite firm or a higher ranked firm.
Can we somewhat think of the monoculture as because of the correlation, it becomes like some sort of a centralized matching, whereas polyculture is distributed.
Exactly. That's one way to think about it. The other way is if firms have monoculture, they have to compete with each other. Right? So they're competing with each other for all the applicants.
So how much of this is because of the uniform preference over?
Great. So theorem one fully extends for arbitrary preferences, arbitrary capacities, arbitrary everything.
Okay,
We haven't thought about theorems 2 and 3, or we haven't thought about this difference in
so
that.
theorem one is on the firm side, theorem
Yeah.
two is on the, well, okay.
Yeah, so on the firm side, it's like nothing depends on, it's like arbitrary setup and everything extends. We haven't thought about it on this side. Simulation wise, it basically holds. Simulation wise, sort of applicant welfare as well. Yeah, sorry, we haven't thought about it mathematically. In simulation and empirics, the same thing holds. And then the last fact is also similar, maybe not hard, is if you're giving some people more lottery tickets than other people, as polyculture does, in any job site, any application site, any real world application setting, some people apply to way more than other people. And that can be because of application fees, that can be because of time, that can be because of all sorts of reasons. And what's happening with independent noise, like something like interviews, is the people applying to more places get more lottery tickets. With monoculture, everyone gets one lottery ticket no matter how many places they apply to. And so that way you're more robust to disparities. And so sort of hopefully this gave one sense of at least what's really exciting me now, which is a lot of intuitions when we analyze a single machine learning model or a single algorithm change when we're analyzing many, right? So sort of part of why I think it's important to really consider these sort of population level effects, sort of not just what's happening when you change one decision, but when you're changing thousands of decisions simultaneously. We're now sort of trying to see if LLMs are correlated in sort of a labor market setting. It turns out they are. So in this case, each row and column is an LLM model or an existing NLP-based job resume scanner. Some of them are really bad. And then sort of you see this correlation structure pop out where sort of models by the same companies and larger models are more correlated with each other.
So this is true if noise is correlated across firms, right? But it has, like, you could still have issues if noise is correlated across applicants.
Yeah. So some applicants could truly just be better than, we were talking about this last night, is like, that's the central empirical, like, this is why this isn't a paper yet, is like sort of, I think you have to do like a little bit more to being like, is this correlation because they're truly correlated conditional on ground truth? Or this is like, this matrix is the unconditional. This matrix is just correlation overall, not conditional on ground truth. What you actually care about is conditional on ground truth.
I guess I might have missed this, but the variance of the noise, this is all kind of about the correlate, either it's perfectly correlated or uncorrelated. The variance of the noise seems like it would be important here in terms of the precision of the model estimates.
Yeah, so some models are just bad.
Yeah, so
Yeah.
do you think that this would extend if you have polyculture, but like some models are better than others, so they have different variance, like the noise term is different and lower variance?
Yeah, so that's definitely happening here, right? So like some models that are here are really bad.
Yeah.
And they just systematically have less correlation, right? Like that's another like interpretation, is like we have all the raw data now. And sort of exactly being like, okay, what about conditional on truth? What about different accurate? Like, how do you actually go from this raw data to, are they correlated, right, to actually answering that question that I had at the top, it requires a bit more work.
Do you think it'll change the?
I don't think
model
so.
In the previous part? Like, figure-
No, not, so the theoretical results extend.
Okay, to like.
Yeah, the theoretical results extend.
Is conditional on ground truth, like, really well defined across multiple firms? Because shouldn't we think of firms as having different ground truths of quality for a given applicant?
Yeah, it's a great question. So what we did here was, well, so here we said the same, so like basically in this simulation, we gave, sort of, we had a resume set and a job description set. And we gave the model the same job description, and then we asked it to rate the same resume. So the models were seeded with the same job description. And this is correlation conditional on sort of that job description. And the same thing roughly holds if you like have like true false question or like multiple choice questions with the real answer.
But
What's the ground truth?
Oh, like a hand label. Yeah, which is exactly like, so you might be worried that hand label is not a good ground truth, and that's what we're worried about. But the same pattern holds if you use real question, like sort of like benchmarks that have a real, like, or at least if you believe the benchmark, the person who answered the benchmark question, they have a label that says here's the right answer out of A, B, C, D.
Yeah, I about I guess more like the previous
Yeah.
papers. Do you think there's settings where the capacity constraints are not like totally fixed? Like they're sort of like,
Yeah.
they're also responsive to what the firm thinks the distribution quality is, right? And if there's a lot of high quality people, they'll try to expand capacity. Like, yeah, anyway, I can like speculate.
Yeah, I think that's one. The other way it could not be fixed is like congestion is a thing, right? Like sort of, if you have 1,000 applicants, you have to sort through to actually get that yield. Sort of, you might accept for your, right, like anyone who's done PhD admissions sort of sort of can attest that like capacity is like kind of a function of who, like sort of one reason is what you said, is like, you might on the forum say you're only taking one PhD student, but actually admit 3 if there's 3 superstars. But then the other one is like, if you have 100 to sort through, that might, and like, you're worried that they're all gonna go somewhere else, that'll like affect how many you accept. Yeah, so I think that's a good question. We don't have that in the model yet. It's a good, like, I tend to think it's second order, but it will make a difference. Right, and I think that's, in real life, that's why you wouldn't actually want full monoculture either, even for applicants. You would probably want some mix of like, everyone gets maybe 10 offers or something, or like at one stage, you might want to be like, make sure that everyone gets at least one interview. But amongst the people interviewed, there's like firms make the same offers to everyone,
Yeah,
or like something along those lines.
yeah, that kind of makes sense. Yeah, I think like you said, like I sort of believe the result, like just, yeah, maybe this is the kind of the first order thing. That,
Yeah, no.
like, yeah, I can imagine something sort of.
Oh, definitely. Yeah. I think sort of thinking about what the intersection is useful. I'm out of time, so I'll just seed this for discussion for later. We're working with the admissions team of a university you'll never guess, full of Cornell authors, that uses an ML model to prioritize undergraduate applications for order of reading. Historically used race and ethnicity as a predictor to predict whether someone will get in, and use that to order application read. Supreme Court says we can't use race and ethnicity anymore. What happens to the ML model? First, perhaps as expected, there's a large drop in diversity in top ranked candidates. This university was doing affirmative action. On the other hand, negligible increase in academic merit of the top group, like equivalent to difference between a 1470 and a 1480 on the SAT. And then what's I think most interesting is that for if what you care about is me as an individual, what's more important than any of this is just randomness in the algorithm, right? If I bootstrapped the algorithm with different data, basically no one is consistently in the top ranked, right? It's like, there's like 20% of people in in the top, or like whatever, 10% of people in the top decile, very few people consistently remain in the top decile across bootstraps of data. Right, so like arbitrariness is still the dominant effect for individual applicants, right? It's like the noise in the entire system. I'll stop here. And yeah.
I'm also gonna put a QR code up on the screen in a second. If anyone, it'd be great if you could scan it. It's like a 2-question thing just to say that you were here, so we can put in our NSF data and get more funding. Yay.
So when we're comparing the monoculture versus polyculture in the performance of the robustness, are you making an assumption that there are much more applicants than the firm side? I mean, the supplies,
Yeah, so we are making the assumption that there's more applicants than firms, right? In the sense that for like the firm welfare results, which is like, do the firms hire the right people, right? Collectively, do they hire the right people? If they're collectively hiring everyone, then sort of that's a vacuous statement. But the result holds simultaneously for every capacity, right? So like, sort of in the limit, sort of the top 5% of people, sort of if you say your capacity is 5% and the top 5% of people are hired by the firms, if your capacity is 10, if you say 10, right? So it's like a true ordering sort of type result.
yeah.
It's also a cost, it looks like, to the polycultural setting, right? Because setting up, like how do you get that independence in the noise?
Yeah.
Comes at a cost. You have either individual interviews, individual evaluation, something like that. So that's why I guess in practice there's a mix, right? Like
Yeah.
you put a threshold using some monoculture thing and then on top of it. So.
Yeah, so actually that's super interesting. I keep trying, I mean, we've moved on to other things, but I think, so in practice, it's exactly what you said is, there's a threshold based on some easy score, that's probably monoculture, so like SAT or GPA or what university they went to or whatever. And then there's interviews amongst that set, right? So it's effectively saying first there's monoculture and then there's polyculture. Sort of, I think theoretically it's actually pretty easy to show because of what Brian was saying earlier, that you actually want a system with the opposite. You want polyculture where collectively I'm interviewing everyone, right? You want to make sure everyone gets at least one interview. But conditional on getting interviews, sort of, you want to potentially identify best and sort of make sure that everyone who's going to be offered sort of has 5 options to go to, that they don't have just one option to go to, right? So sort of if you combine this like congestion concern where like you can't possibly interview everyone with this like the type of arguments in this paper, I think what you could show pretty straightforwardly is you want the world to be the opposite of the world we live in. And I have no idea how we get there, but right, it's like you can't actually, right, because there actually isn't a way to impose polyculture to decide who to interview and then monoculture after that. Or maybe like, or like LinkedIn could do it, right? LinkedIn could do it in their recommendation system for at least polyculture at the recommendation stage, right? They could just give people different recommendations.
So I'm curious more about how to think of this. So in this case, it's the firms decide.
Yeah.
Right. And in like the matching market, it's like neither the firm nor the other participants decide. And then I don't know if there's one for like the whatever job employees, seekers would decide, but like whoever the decision is incident on, does that matter to this? Like in how we think, how you're thinking about like matching markets versus recommender systems and.
Yeah, that's a good question. Like, I mean, so one, I think in this model, it's not quite firms deciding. We assume applicants rank according to their true preference. Firms rank according to a noisy preference, and then sort of stable matching is run.
I see.
And you get sort of, and it turns out in these large market models, sort of the equilibrium is unique. And so it's not like there's multiple stable matchings. And so you don't actually have to think about which side is like sort of, is one side proposing or whatever. So it's actually, yeah, so, but yeah, it's a good question. It's like this question of who is actually deciding is, I think, is actually exactly where this intersection of the two fields, I think, comes in, that I'm super interested in. So like, I think what's happening in school matching is, people, so like, on the school side, the rankings are some policy, right? The city decides we're gonna use, cities and schools decide they're gonna use some combination of grades, test scores, location, and income-based diversity preference, right? That's a law. And so that's gonna set school side policies, rankings. Student side is like some weird, like, information acquisition sort of search process. But at some point, they're gonna give a ranking. And then the city's gonna decide. But if you think about it not as they give a ranking and the city decides, but in the search process, and let's say you can give a recommendation. So now suddenly you're recommending 10 or 15 schools to them. Now they are deciding sort of which 5 to apply to or 10 to apply to. And then there's a second stage. So I actually think like a lot of systems secretly have this pre-matching stage where the internet, family, consultants, counselors, everyone is giving advice. And then whoever's ranking is deciding from that advice. And I think that stage is super interesting and important to study.